So when we talked about proof 002 last time, I was encouraging us to look at, and this is always a good idea, look at the logical content of the statement that we're trying to prove. It begins with an antecedent, a hypothesis. X and y are both odd numbers. X is odd and y is odd. So we're going to call that proposition P. You see the word then in here, which we'll transcribe as the little forward implication symbol. And then we have the consequent, the conclusion of the theorem. The product xy is odd. And so we'll call that Q. So we're supposed to prove that P implies Q. And as was written in the presentation, so helpfully at the beginning of the presentation that we saw on Monday, if we were to prove this directly, we would begin by assuming that P is true. Now, assuming that something is true is an awesome thing in a proof because it gives you something to work with, right? If I assume that x and y are both odd numbers, then I know something about x and y. I know the definition of what odd means, and I can plug that definition in to say something about x and y. So assuming that P is true lets us take that tool out of the toolbox. It gives us something on the table. What it doesn't give us, and what we then need to do, is we need to deduce the truth of the consequent Q. So we assume P, we get P for free, and then we have to demonstrate that Q necessarily must also hold. So that was the direct proof. That was what we saw in item 001. And I'll be honest, I think that the direct line of attack for this theorem is probably the more natural way to prove it. The indirect proof of this statement is, I think, probably considerably more challenging for reasons that I think we'll see in a minute. So with an indirect proof, we actually have two possible lines of attack: contrapositive, proof by contraposition, and contradiction, proof by contradiction. And I want to talk a little bit about those as methods of approach and talk about what are some of the benefits and drawbacks of doing a proof in one of those fashions or the other. So starting with a proof by contraposition, what would it mean to prove a statement P implies Q by contraposition? What do you do in that?
Negation, well, you assume negation P to negation, negation Q to negation P.
Okay, right. So we're going to assume that Q is false. In other words, we're assuming the negation of Q is true. So that's what we get on the table in a proof by contraposition, is we automatically out of the box get to assume that Q is false. So in this case, we would start by assuming that the product x times y is even. Right? So that's what we would get on the table. And then what did you say we then have to deduce? What do we have to prove if we're going by contraposition?
Negation of P.
Yeah. Deduce that P is false. So what we're really doing in a proof by contraposition is we actually have the same structure of a proof here as we did in the direct case. We assumed something and we proved something else. We assumed something, we proved something else. And those things were directly related to our original P and Q. So what contraposition really is it's a direct proof of the contrapositive of our original statement. So it's a direct proof of the logical implication not Q implies not P. Right? So sneakily, it is an indirect proof of the original statement, but it's a direct proof of the logically equivalent contrapositive of the original statement. Okay? So that's a proof by contraposition. It's nice because it's parsimonious. It doesn't require us to bring in additional logical statements that we have to worry about. We can worry again just about Q and just about P, right? Working with their negations, but still. So that's one fashion of indirect proof. The other fashion of indirect proof is a proof by contradiction. So what happens in a proof by contradiction? What do we get to assume? And what do we then have to deduce? What's that logical structure look like, Ryan?
We assume that the hypothesis is false.
Assume that the hypothesis is false. So P? Yeah, not P. Yeah.
Assume Q is false.
So we assume Q is false, which is also something that we do in a proof by contraposition. Okay. But we also have to assume something else. When we're proving by contraposition.
P is true.
Right. So assume that P is true and Q is false. So I'm going to clear this out here and think about this in a different way. What we're really doing is that we're assuming, and this is going to blow your logical minds for a second, we're assuming that P implies Q is false. Right? We're assuming that the entire statement of our theorem is false. So we're entering this alternate universe where the thing that we're trying to prove is true, the whole implication of the theorem, we're assuming that the whole theorem is false. Now, the only way to falsify an if-then statement is to do what? Like if I claim that if it's raining, then I have an umbrella, how do you prove me wrong? If I'm telling you that every time it rains I have my umbrella with me, how do you prove me wrong? What is sufficient evidence to prove that it's not true that if it's raining, then I always have an umbrella? If I, no, having an umbrella isn't going to disprove that if-then statement, right? If I'm telling you every time it rains, I have my umbrella with me, how do you prove me wrong?
Prove that it's raining and then it will be.
Right. To prove me wrong in a court of law, you would have to say, on the night of July the 31st, it was raining and you didn't have your umbrella with you, sir. I have evidence, right? That's how you would prove me wrong in that if-then statement. You would have to show me that it's possible for the premise to be true, but the conclusion to be false. That is the only way to falsify an if-then statement. And that's exactly what we're doing when we set up a proof by contradiction. We assume that the implication, P implies Q, is false, which means assuming that P is true, but that Q is false. So in the case of item 002, what would that assumption look like? How would we state that assumption in this specific case? Serena.
For all integers x and y, so if x is odd and y is odd and their product x, y is even.
Right, so we would start by saying, let's assume that x is odd and y is odd, so we're affirming P, but that x, y is even, so we're denying Q. Affirm P, deny Q. So we're going through the looking glass to a place where this theorem is false because there exists a pair of odd numbers, x and y, whose product is even. Okay, so one of the nice things about contradiction proofs is we get a lot of information on the table to work with. In the other forms of proof, we only got to take off of the shelf one piece of information. Either we assume that P is Q and that's all we have to work with, or we assume that Q is true and that's all we have to work with. But in a contradiction proof, we get two things we get to assume are true. So we have more information on the table to work with. Sometimes that's what it takes to get to where you're going. But if we have all that information on the table, what do we deduce? What do we need to deduce in a contradiction proof? Where are we going with a proof by contradiction? What is the contradiction aspect of a proof by contradiction?
We're almost trying to prove ourselves wrong so that we can prove the proof correct.
Exactly. We're trying to prove ourselves wrong. We're trying to show that the assumption that our theorem is false leads to a contradiction, leads to a statement which cannot logically be either true or false, which necessarily must follow from the assumption that our theorem is false. The problem with proof by contradiction, sometimes the fun, the thrill of the chase in a proof by contradiction, is you might not know up front what that other statement is that you're going to have to show is a contradiction. So deduce that some other statement R is both true and false. True and false. And this R, again, you might not know what it is up front. It's some possibly unrelated to P and Q. Right? So if you're trying to, well, we'll see this when we talk about 003. This R is sometimes something very simple. Sometimes it's something that's totally, you would not have expected that this is what you end up falsifying when you prove something by contradiction. But these are our three tools in our toolbox, our three methods of proof. And they each have their own benefits, they each have their own drawbacks. You might not know at the beginning of working a proof which one of these is going to be the one that your theorem yields to. So really a lot of the creative process in mathematics of discovering proofs is feeling your way through one or more of these methods and figuring out which one of them is going to be the one that gets you home.